All right, let's think big. Let's think about the biggest circle that we are very, very familiar with. Let's think about the Earth going around the sun. Now ask yourself, what causes the Earth to go around the sun? We know that there has to be a net force pointed towards the center of the circle. After all, that is the centripetal force, and that is the thing that causes us to move in a circle. But what force is it? Is it an applied force? Is there something outside of the Earth that is pushing on the Earth with like a hand or something? No. Is it a normal force because we are going around a track and that track is pushing us towards the sun? No. Is it a friction force? Are we sliding against something? No. Is it a tension force? Is there a rope between us and the sun, and is the tension in that rope that is causing us to move in that circle? No. The only thing that causes us to move in a circle is the force of gravity. Some say that there is no gravity in space. I'm here to tell you there is. Gravity is a long-reaching force, and gravity from the sun is what causes us to move in a circle around the sun. So if we wanted to draw a force diagram for the Earth, the force diagram for the Earth might look something like that. It is a force that is pointed directly towards the center of the sun. Now, we currently have an equation for the force of gravity. We came up with it in semester 1, right? Fg equals 9.8 newtons per kilogram times mass. Now, we did an experiment where we came up with that equation. If you recall, we had a bucket attached to a spring scale. We kept putting masses into that bucket, and then we were measuring what force the spring scale read. So we then created a graph of mass on the x-axis and force of gravity on the y-axis, and we found that there was a linear relationship between those two things. And the slope of that line was 9.8 newtons per kilogram. So when you write the straight line equation for that line, you get Fg equals 9.8 newtons per kilogram times mass. That's how we got that equation. But we got that equation because we did this experiment on the surface of the Earth. If we repeat that experiment somewhere else, somewhere maybe on the moon, maybe on Jupiter, maybe on Mars, anywhere that is not the surface of the Earth, we're not going to get that same slope of 9.8 newtons per kilogram. That 9.8 newtons per kilogram is particular to the surface of the Earth. But the last part of this unit is us investigating space, and so we're not going to be on the surface of the Earth anymore. We can't use Fg equals 9.8 newtons per kilogram times mass when we talk about the force of gravity due to the sun on the Earth. So what we're going to have to do is we're going to have to break open that 9.8 newtons per kilogram. We're going to have to be able to see what's inside, and hopefully out of it we're going to get some kind of universal law of gravity that can be applied to anywhere, anything, any place, any time. Now the good news is somebody who's pretty smart has already thought about all of these things. Who was that? It was Isaac Newton. He recognized a few attributes to the force of gravity. Number 1, the force of gravity is proportional to the mass of both objects. What do I mean by that? Well, let's pretend that we have two different objects here on Earth. Maybe we have some kind of big object, and then we have some kind of small object. Would they have the same force of gravity? Of course not. The big object would have some kind of a big Fg, and our small object would have some kind of a small Fg. So it's very clear to us that the mass of our object affects our force of gravity. But there's another object in that interaction, and that is the Earth. So if we think perhaps about that big object on Earth, would that big object have the same force of gravity acting on it if instead it was on the moon? No. It would have a bigger Fg when it was on the Earth, and it would end up having a smaller Fg when it was on the moon, because we know that the force of gravity on the moon is smaller than on Earth. So it's not just our object that matters, it's also our planet that matters. And if we think about it, a planet is really just another object anyway. But out of this thought experiment, we can see that the force of gravity is proportional to, not equal to. We're going to use the Greek letter alpha as a way to say proportional to the mass of object 1 times the mass of object 2. The second thing that Newton noticed, he recognized that the force of gravity decreases as the center-to-center separation. And I'm really going to emphasize we need to always be talking about the center-to-center separation. He realized that the force of gravity decreases as the center-to-center separation between the two masses increased. And not only is it an inverse relationship, but it's an inverse squared relationship. So let's talk about another example here on Earth. If we maybe think about things falling on Earth, like perhaps, I don't know, an apple falling out of a tree, we know that that apple is going to accelerate towards the Earth. It accelerates at 9.8 meters per second squared, right? Yeah, we know that. But you know, our moon is also accelerating. So if we think about the Earth, and then we think about the moon way out here, the moon has a centripetal acceleration towards the Earth. And that centripetal acceleration is 0.00272 meters per second squared. So our acceleration, when we increase our distance, right, we're increasing our distance a ton. If we think about that center-to-center separation between the Earth and the apple, we're really talking about the separation, between here and here. That separation is just the radius of the Earth. If we want to increase that separation, so now we're going from the center of the Earth to the center of the moon, that separation is 60 times larger. So it's 60 radius of the Earth. So as we increase our separation, we have decreased our acceleration. And we're using acceleration here as a proxy for force because you know from Newton's second law that F net equals ma. Whatever is happening to our acceleration, we can say that that same trend is happening to our force. So it's very easy to see that this is an inverse relationship. But Newton recognized that it was actually an inverse squared relationship because if you take that 9.8 meters per second squared of acceleration on the surface of the Earth and you divide it by 0.00272 meters per second squared, which is the acceleration of the moon, you're going to find that that is equal to 3,600. That ratio is 3,600. What is 3,600 compared to the radius? Well, 60 squared is equal to 3,600. And that exactly matches the fact that the separation between the Earth and the moon is 60 times greater than the separation between the Earth and that apple that's at the surface of the Earth. So that's how Newton was able to recognize that it is not just that the force of gravity is proportional to the inverse of the separation, but he was able to recognize that it's proportional to the separation squared, or the inverse of the separation squared. Third thing that Newton realized, he realized that if you wanted to progress this proportionality to an equality, you needed to have some kind of a constant. So what we are going to do here in exercise 1 is we are going to figure out what that constant needs to be. So what we know right now is that the force of gravity is proportional to the mass of our two objects divided by the separation squared. To progress that into an equality, so I get to write an equal sign here instead of that lovely alpha, we need to have some kind of constant, which we're going to use the big G to represent that constant, times m1 times m2 over r squared. And this is going to be our job to find this constant. In order to find this constant, we're going to have to think about the surface of the Earth. We know that on the surface of the Earth, our force of gravity is 9.8 newtons per kilogram times mass. So this 9.8 newtons per kilogram times mass must equal our constant times the mass of object 1 times the mass of object 2 divided by our r squared. If we look at this, we see that there is mass on the left-hand side of the equal sign, there is mass on the right-hand side of the equal sign. Is it possible that some mass is going to cancel out? Well, things to remember is that one of these masses needs to refer to the object, and one of these masses needs to refer to the planet. So is it our object mass that will cancel out, or is it our planet mass that will cancel out? Well, you know, in good old regular 9.8 newtons per kilogram times mass, the mass there is talking about the object. So it is the object mass that cancels out. And so we are left with 9.8 newtons per kilogram is equal to our constant times the mass of the Earth divided by the radius of the Earth squared. In this problem, I give you the mass of the Earth, I give you the radius of the Earth, although I'm going to warn you right now that this is the last time I'm going to give you these two numbers. Physicists assume that you know a certain amount of information, and physicists assume that you know the mass of the Earth and the radius of the Earth. Is it very reasonable to know those two things? Maybe yes, maybe no. But I'm going to tell you right now that you're going to have to know this information for this class. So know that the mass of the Earth is 5.972 times 10 to the 24th kilograms. Know that the radius of the Earth is 6.371 times 10 to the 6th meters. All right? Because with those two numbers, we can fill in everything about this equation except for our unknown constant. So we're going to do g times 5.972 times 10 to the 24th kilograms, and we are going to divide it by 6.371 times 10 to the 6th meters, and don't forget to square it. Once you do this algebra, you find that our constant g is approximately 6.67 times 10 to the negative 11th. And the unit for that would be Newton meters squared per kilogram squared. And that's a really funky unit because its only purpose is to make sure that it cancels out all the other units and leaves us with newtons, which is what it does. Anyway, but this 6.67 times 10 to the negative 11th, this is something else that I think you should memorize because this is called the universal gravitational constant. And it is this universal gravitational constant that allows us to create a universal law of gravity that is going to be able to work anywhere, anytime, with any masses to find a force of gravity between those objects. So what I'd like for you to do is I'd like for you to flip the page. I would like for us to write out that universal law of gravity. Fg is equal to big G times m1 times m2 over r squared, where big G, the universal gravitational constant, is equal to 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. So let's take this time to actually talk about what 9.8 newtons per kilogram really is. We've now realized that it's particular to the surface of the Earth, and if we want to break that thing open, we actually find that inside of it is a whole bunch of stuff. Inside of that 9.8 newtons per kilogram is everything that is not the mass of your object. So all of this was trapped inside of that 9.8 newtons per kilogram. Now, this is actually referring to something called the gravitational field, which can kind of be thought of as a tractor beam. It pulls masses towards each other, and the effectiveness of that tractor beam increases as the separation between those two masses decreases. Okay, now this is frequently represented by a lowercase g in textbooks. So if you ever see g, you should know that that's referring to the gravitational field. And for the surface of the Earth, that's referring to 9.8 newtons per kilogram. It refers to different numbers on different planets because not every single planet has the exact same gravitational field as Earth. So don't just always take G to mean 9.8. It can be different on Jupiter, different on Mars, different anywhere that is not the surface of the Earth. Okay? All right. So let's do 2 more examples, and then we'll call it a day. So a 1,000 kilogram satellite orbits the Earth in a circular orbit at an altitude of 1,000 kilometers. What is the force of gravity on the satellite? Draw a quick picture. There's Earth. Here's our satellite. They're trying to tell us that the altitude is 1,000 kilometers. Now we measure altitude from the surface of the Earth. So it is only from the center of the satellite to the surface of the Earth that is 1,000 kilometers. And by the way, 1,000 kilometers is 1,000 times 10 to the third meters. And since we love to work in kilogram, meters, and seconds, I'm just going to make that change right now. We are going to have to add to that the radius of the Earth because we are going to want to use the center-to-center separation if we are going to use the universal law of gravity to solve this problem. So the center-to-center separation, or sorry, the radius of the Earth, again, I'm not going to give it to you because I'm going to assume that you know this, is 6.371 times 10 to the 6th meters. So when we write out this universal law of gravity, Fg equals g m1 m2 over r squared, and we start to fill in these numbers, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared, times the mass of the Earth, which again, I'm not going to tell you, I'm going to assume that you know it's 5.972 times 10 to the 24th kilograms. And then the mass of our object, 1,000 kilograms. We're going to divide all of this by our center-to-center separation. So we're going to take that 6.371 times 10 to the 6th meters. And we need to add to it that altitude, 1,000 times 10 to the 3rd meters. And don't forget to square it. It's a whole lot of exponents, and you're going to have to be very aware of what you're typing into your calculator. Make sure you use parentheses effectively because we need to use the correct order of operations in order to get the correct answer of 7,331 newtons as the force of gravity. Let's do one more. A 270 kilogram communication satellite is placed in geostationary orbit 35,780 kilometers above a relay Earth ground level. So basically, it's just describing to you that 35,780 kilometers is the altitude. What is the speed of the satellite in orbit? So again, let's draw a picture so that we keep everything straight. We got the Earth. We got this satellite. We got that from the Earth to the surface of the Earth is our radius of the Earth, 6.371 times 10 to the 6th meters. And then from the surface of the Earth out to this satellite, that's another 35,780 times 10 to the 3rd meters because we want everything to be in meters. Everything, everything, everything. Now we want to know the speed of the satellite, so that says to us, we're probably going to want to use mv squared over r. So since we know that mv squared over r is a way to calculate fc, we got to think about what is the force that is making us move in a circle. Well, it's just the force of gravity. It's the only thing out there. So we can say that mv squared over r has to equal the universal law of gravity, because again, we're not at the surface of the Earth. So we're going to put in G times m1 times m2 over r squared. Hopefully what we notice here is that we've got some stuff that will cancel out. Things like the mass of the object, right? This was the object. Just remember that. Also, we've got an r in the denominator on both sides, so we can get rid of those r's as well. And what we are left with is we are left with speed squared equals big G, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared, times the mass of our object, or of our planet, right? So 5.972 times 10 to the 24th kilograms. Since we're talking about the Earth, that's the planet. And we're going to divide that by our separation. And in this case, our separation is the radius of the Earth, 6.371 times 10 to the 6th meters, plus 35,780 times 10 to the 3rd meters. And once again, this problem becomes a plug and chug problem. We just need to do the algebra to find that the speed of the satellite is going to be 3,074 meters per second. Wow! It's really fast. We really move fast up there in space, don't we? That is actually a completely realistic answer. So don't be afraid of big speeds when we're out in space, because we got a lot of ground to cover.